The next type of integral that we will explore is the surface integral with a scalar function. And later we'll look at the surface integral with a vector field, but we'll start off with a scalar function. Now, remember we looked at line integrals in the past involving scalar functions, and what we did was we were given an integral, a single integral, and we were asked to evaluate this integral over a path. And so that's the name line integral, except it was a curve. So we integrated over a curve. Well, now we're going to be given an integral, and actually it will be a double integral, and we're going to be asked to integrate over a surface. Now, this is going to require us to think back to when we explored a surface area. When we were studying double integrals initially, one of the things we looked at was, well, how do we find surface integral using double integrals? And what we noticed was, if you have a surface defined this way, like z equals g of x, y, and it could be z equals x plus y, z equals x squared plus y squared, whatever, we said that you could find the surface by thinking about the projection down from the surface to the xy plane. And we could think about, up from that, so we've got a region down the xy plane like this picture. And we said that what we'll do, the game we'll play is, we will think about a tangent plane at a point. Maybe down here we would have this point xi, yi. And we project that up into the surface, and we say, okay, at that point in the surface there's a tangent plane, and we know how to, and what we did was we partitioned that tangent plane in so that we had a small parallelogram with this maybe at the corner of that parallelogram. And we said this, we said, well, if I can get the area of that parallelogram, that's approximately the surface area. And we know how to get the area of the parallelogram. We used a cross product, and we came up with something like this. We said, well, let's call this the change in surface sub I. We said, well, that's going to be equal to g of xi, yi, the partial of that with respect to x, plus the partial with respect to y, plus 1, and these are squared, dA. Let me put I here, okay? So what we did was we said, okay, if you want to look at this little parallelogram up here, this is the area of that parallelogram. And then, of course, if we add up those areas, using integration, what we get for surface area is this. Well, we get ds, which could be written this way, over this region. We get the square root of gx squared plus gy squared plus 1 dA. Okay, so that I went through that very quickly because just to remind you, okay, ds, this ds is this right here. Now, what we want to do is we want to say, well, then what is a surface integral? Well, the surface integral is going to go like this. We're going to have this double integral, but instead of just the ds in there, we're going to have a function. And then the ds. Okay? So we're taking the function times the ds. Now, so we've got this integrand here, this scalar function, and we want to integrate over this surface. And by the way, this is not r, this is s here. So we're going to integrate over the surface. So this is just a general form for a surface integral of a scalar function. Now, we've got this. We've got z is equal to g of xy. We've got this surface, and what we want to do is we want to go ahead and evaluate this integral. So here's the way we proceed. we take this double integral, and I put in the x, the y, and in place of the z, I'm going to put what z is so that we'll be sure. And we're looking at z values. We're looking at this surface. In other words, we're restricted to this surface. So we're integrating over the surface. So in place of z, I'm going to replace the formula for z, g of xy. Then in place of ds, I'm going to put gx squared plus gy squared plus 1 dA. And dA is going to be something like dx, dy, dy, dx, or we could be in polar form. But this is how we're going to evaluate a line integral. So I've got this function here. I'm on this surface, so I replace z with that formula for that surface. Okay, so let's look at an example. I want to evaluate this line integral, and here is my surface. Now, here's what we want to do. We want to solve for z, because remember, we're going to have this form. So I want to solve for z, and what I'm going to get is 6 minus x minus 2y. Now, that's what g of xy equals. So this is g of xy. So now, here I go. I'm going to say, okay, the partial with respect to x is -1. The partial with respect to y is -2. Okay? So now I'm ready to set up my integral. I've got y squared plus 2y, and in place of z, I'll put what z is. Z is 6 minus x minus 2y. And then I need to put the rest of it. So I've got this. I've got -1 squared plus -2 squared plus 1 dA. Kind of ran out of room here. Now we're not completely finished because, of course, I need to simplify this and get my bounds of integration, but this is kind of the setup. Notice I replaced the z with what z is equal to, and then over here I have the ds. Okay, now let me get a little bit more room here, and I'm going to leave myself room for the bounds this time. But here's what I have. I have y squared plus 12y minus 2xy minus 4y squared. And this integral, it looks like it's going to be the square root of 6. So let me just put that on the outside like that. So notice I just distributed the 2y through and got this. Now this isn't something that's easy for us to integrate, but what we got to do is we have to get the bounds of integration. Now remember, this right here, this was my surface. This was my surface. Projecting down on the xy plane, you get x plus 2y equals 6. So the z is 0. So you get x plus 2y equals 6. Okay, so let's look at that. Okay, so here I go. Down here, here's x, and here's y. X plus 2y equals 6. So when y is 0, x is 6. Yeah, right there. 1, 2, 3, 4, 5. Yeah. And then when x is 0, y is 3. So on the xy plane, we're integrating on this little triangle here. So what we can do is I can say, well, let me integrate with respect to x first. If I integrate with respect to x first, I get 6 minus 2y. So x goes from 0 to 6 minus 2y. Okay, now I've taken care of the x. Well, what is y? So see, no matter how I fix y, x is going from 0 over here to the function for all the values for y. Now, as far as y goes from 0 to 3. And then, so I'm integrating dx dy. Now, this is just a regular double integral that we have no problem evaluating. So once we get to this point right here, it's just a straightforward. Now look, here's the thing. For this particular problem, notice we had our surface defined g is equal to xy. We don't have to have it that way. In other words, when we had z is equal to g of xy, and we looked at our double integral, we had f of x, y, g of xy, and then we had gx squared plus gy squared plus 1 dA. Okay, so that's that. Now, let's suppose that our surface is given to us this way. Let's suppose that we have x equals g of yz, like that. Well, then we're going to have a little bit different looking integral. We're going to have f of, in place of x, g of yz, y and z, and then the square root gy squared plus gz squared plus 1 dA. So there we're projecting it onto the y, or into the yz plane. Now, finally, let's suppose I have y equals g of xz. Well, then we have f of x, g of xz, and z, and then we have gx squared, gz squared, plus 1 dA. So those are the different types that we could have. So in other words, the problem is worked the same way. Things just look a little bit different.